For the graphing motion introduction notes and mainly focus on position time graphs. So starting off for graphing motion, that's what this whole first unit is going to be about. And the reason that we as in physics class look at motion graphs is because they're a great way to convey a lot of information in one image. So they describe the real world events such as a person walking or a car driving is a lot of the scenarios that we'll focus on in physics, keep it kind of simple. And we'll put all of this information about the car speeding up, slowing down, how far it travels, how much time it goes for, if it's keeping a constant velocity, all of this stuff we can put in one compact image instead of reading off like a whole paragraph of describing what it's doing. All right, so it's just very compact, and we're going to work through this unit of breaking that down and being able to analyze them as well as construct them. All right, so there are three types of motion graphs we are going to study in this unit. The first is a position time graph. It's also called a distance time graph or displacement time graph or other terms. But I try to stick with just calling it a position time graph, but if you see those other terms, it's the same thing. Right. Next up is a velocity time graph, and then we have an acceleration time graph. These are examples of what they look like, and they can all be used to convey the same information. It just depends on what information you're plotting on the graph. But we can take a distance time graph and figure out what the velocity was. We can, if we have a velocity, we can figure out what the distance it went and things like that. And we'll be learning that through this unit. All right, some definitions to go over just so we're all on the same page before we get going. The first term is displacement. You just heard me mention this on the last slide. Displacement is the distance between where an object started moving and where it ended moving within a frame of reference. So, for instance, your total distance you travel when you're walking around school. Let's say you start at your first period classroom on the front hallway, and then you end up in my classroom, which is in the back of the building, and then third period you're back on that front hallway in the front of the school. So you've walked, let's say, 100 meters total, 50 meters from the front of the school to the back, and then another 50 going back to the front. Your distance traveled would be that 100 meters total, 50 each way. Your displacement, however, if you ended up back in the exact same spot in the front of the building, your displacement would be 0. Okay, so like think of like a track. You're running in a circular track. You run your race and you end up in the exact same spot. Your displacement is 0. If you run halfway around the track, your displacement is from where you started running to where you stopped, directly like through the center, not like around the curvature of the track. Okay. All right, next term is position. Position is simply just where this object is located at that point in time. Normally we're thinking linearly, like going straight forwards or straight backwards. So like where is the position located in reference to like a starting line or spot 0. Right. Velocity is the speed or how fast an object's going, as well as the direction the object is going, whether it's going forwards, backwards, left, right, east, west, north, south, that kind of thing. And then the term acceleration means the rate at which the velocity of an object is changing. So if it's speeding up or slowing down, you can have a positive acceleration or a negative acceleration. A lot of times you want to say the word deacceleration. That's technically not a term. I do let it slide. But when you think of deacceleration as in slowing down, that's technically considered just acceleration. Okay. And then the last thing is slope, which you hopefully have learned in a math class by now. But slope is simply the steepness of the line. We're going to review the formula for that here in a little bit. All right. So moving on, our first type of motion graph is a position time graph. A position time graph represents the location of an object during a segment of time. So we're plotting where the object's located, and if you think of it like from a starting point, where it's located from that at a certain time period. And normally we'll work with things in seconds. The motion of the object can be analyzed by looking at the shape and the slope of the line. So here we have a position time graph. Unfortunately, my labels got cut off, but there should be a little X right here to represent a position time graph. And you can see 0 as our X-axis. That's where the object started at. It went up to 4 meters in 5 seconds. Then it dropped down from 5 to 10 seconds. The object went in the negative direction, and then it stopped moving. And we're going to talk about what these different shapes and slopes mean. So the slope of the line tells you the velocity of your object or how fast it's going, as well as what direction it's going. So if you have a negative slope, once you calculate it as negative, or you just look at it and you say, okay, on this graph right here on the previous slide, I know from 5 to 10 that's a negatively sloping line, then that means your object is going in the negative direction, and or you could say it's going backwards, but it would have a negative velocity and a negative direction. If your line is positively sloping or going up on the graph, it's going to have a positive velocity and be moving in the positive direction or forwards direction. If the slope is 0, then it's not moving at all. It's just sitting still at that spot in time. So on this previous graph, from 10 to 15, it's just sitting at -4. So if you think of this as like a starting line on a track as your x-axis is 0, then this person would be, say, 4 meters behind the starting line, just standing there. Okay. All right. And then last on here, we have our slope formula. This is hopefully a review from your math class, but it's your change in y over your change in x, or delta y over delta x is the very formal way to put it. We can break that down. The delta symbol here, that's a Greek letter, is the triangle, means your second y point minus your first y point divided by your second x point minus your first x point, or simply put, in easy terms, rise over run. Okay, so you're going to divide how much up or down the line goes by how far over the line goes. Okay, and we're going to practice that here. All right, I don't have these things worked out on the slide, but we're going to talk about this. So this is just a check for understanding to review calculating slope and some other questions here. So the first one, using this graph, we're going to calculate the velocity from 0 to 3 seconds. So we have a position graph. Our slope is rise over run. So from 0 to 3, our line happens to start at 0 for the rise, or the vertical. It goes from 0 up to 6. So our rise here is 6. And then our run here goes from 0 to 3. So it goes over 3. So our run is 3. So 6 up and 3 over. So 6 divided by 3. Our slope is going to be 2. For units, we need to make sure we include the units for velocity. For what we're going to work on right now, our velocity units are always going to be meters per second, to keep that part of this simple. But you're technically getting that meters per second for the velocity because you're dividing your rise, which is measured in meters, by your run, which is measured in seconds. So it's meters divided by seconds. Those don't cancel out, so you're left with meters per second. So your final answer for number 1 is 2 meters per second. Okay. For number 2, we're calculating the velocity from 5 to 8 seconds. So we're going to look at this line right here. Now we can see this line is going down on the graph, so that would be a negative slope. So our answer here, we want to make sure, is a negative answer. Our line for the rise is starting at 6 on the vertical and dropping down to 3. So 3 minus 6 gives us -3 for the rise. And it's going from 5 over to 8. So 8 minus 5 gives us a run of 3. So it's dropping, so rise of -3 by a run of 3 gives us an answer of -1. And then again, for our units, will be meters per second. So our full answer is going to be -1 meters per second. All right. So next one, what is the direction of the object from 5 to 8 seconds? And we interpret that from the slope. So we got a negative slope here. So it'd be going in the negative direction. Right? And number 4, during what time segment or segments is the object not moving? So when we're looking for not moving, we're looking for those horizontal lines that have a slope of 0. We can see we have 2 of those here and here. We have it from 3 to 5 seconds, and then again from 8 to 10 seconds. So both of those sections, the object is stopped. Here it stopped at 6 meters away from its starting point, and here it stopped at 4 meters away. Okay. All right, moving on. We've got, now we can interpret the shape of the line that we're looking at. So with position time graphs, you're going to have 3 shapes you can have. You can have diagonal lines, curved lines, or horizontal lines. Diagonal lines mean your object is going at a constant velocity. It's maintaining the same slope the entire time. Like this one here is always sloping the same amount. So it's keeping that constant velocity. If we have a curved line, that means it's going to be accelerating. And we can have some different options for curves. We can have one that's going to get steeper and steeper and steeper as it curves. And like this one, it starts off kind of flat down here, and then it gets steeper and steeper and steeper. And if it kept on going up, it gets steeper and steeper. that means it's speeding up. So if you get steeper, you're speeding up. If you get a decreasing in steepness, it gets flatter and flatter and flatter as you go through the curve. Like here, it's much steeper, and then as you go down, eventually it like flattens out, and as it keeps going, it gets flatter and flatter. You're gonna be slowing down, right? So getting steeper, speeding up. If you're getting flatter, you're slowing down, right? And then the third option is horizontal lines, which means you're not moving. And I don't have a picture of that here. We already talked about this before on a previous slide, right? So let's go over number 8. And again, I unfortunately don't have these worked out on the PowerPoint, but we're going to talk out through them if you want to write them on your guided note sheet. So we're going to go through each one and talk about them individually. So we're going to go over, we're just describing the motion of each of these graphs. We're going to look at the shape of the line and what that tells us, as well as kind of bring in the slope of telling us which way it's going, positive or negative direction. We're obviously not calculating the slope because we have no numbers here to work off of, but we can say, just looking at it, if the line's going up or down, if it's going to go forwards or backwards, or positive direction or negative direction. All right, so for a graph, we have a diagonal line that's sloping upwards. So since it's sloping upwards, that means it's going to go in the positive direction. And then since it's a diagonal line, that tells us we have a constant velocity. Right? For graph B, we have a diagonal line that is sloping downwards. So that means it's going to go in the negative direction since it's sloping downwards. And again, we still have a diagonal line, so we're going to have a constant velocity. For our third graph, graph C here, the line is headed up on the graph. So that means it's going to go in the positive direction. And we have a curve, so that does mean it's accelerating. And with that, we want to talk about which type of, is it speeding up or slowing down? So we're going to look and say, okay, it's flatter here and steeper here, so it is getting steeper. So we're going to have a graph that is speeding up. All right, so our object is going in the positive direction. It's accelerating, as in it's speeding up. All right, for our fourth graph, graph D, we have a curve that is sloping downwards, so we are going in the negative direction. It is a curved line, so there is acceleration, and that curved line is getting flatter towards the end, so it is going to be slowing down. Right. Graph E, we have a curved line going up, so we are going in the positive direction, and it is getting flatter as we go through that curve, so that means we are slowing down, so we do have acceleration here. For graph F, we have a curved line headed in the downward direction, so since it's going in the downward direction, we are going in the negative direction. That curve is getting steeper as it goes through. It's much flatter here than it is at the end. So since it's getting steeper, it is speeding up. So we are speeding up in the negative direction. So these four graph curves here, C, D, E, and F, those are kind of like the four options for curves you have. You have two that are going in the positive direction, C and E, and one would be speeding up, the other slowing down. And then D and F are your two options for going in the negative direction. You have one that's slowing down and one that's speeding up. Right? Our last three graphs are all pretty similar. They're all horizontal lines. This one, it's hard to tell, but it is on the x-axis. You have one above the x-axis and below the x-axis. But all of three of these are telling us the same thing. The object is not moving. The only difference is where that object is stopped at. This one's stopped like on your starting line. This one's in front of the starting line, and this one's behind it. All right. So, all right. Let's go over the last check for understanding. So we're talking about this graph here. We are going to, during which time segment or segments is the object not moving for number 1. So when we're not moving, we are looking for a horizontal line. So we have that from 4 to 6 seconds. So for number 1, our answer is 4 to 6 seconds. All right, number 2, moving in the positive direction. So to find something moving in the positive direction, we are looking for a line that is going up on the graph or sloping positively. So we have 2 sections. We have 0 to 4 that's doing that, as well as 6 to 8 seconds that are moving in the positive direction. For number 3, moving in the negative direction, we are looking for something going sloping negatively or headed down on the graph, in which case from 8 to 10 seconds, we have that. All right. For number 4, when we are slowing down. So for slowing down, we are looking for a curved line that gets flatter towards the end. So we have 2 curves here from 6 to 8, and then it changes at 8 seconds and starts going back down. So we want to look for which one's getting flatter. This one on the end here is getting much steeper versus 6 to 8, we're getting much flatter at the end. So for slowing down would be 6 to 8 seconds. And then for number 5, speeding up, we're looking for it getting steeper, which we have from 8 to 10 seconds. And then lastly, we're number 6 has a velocity of 2 meters per second. So in order to find velocity on a position time graph, we need to calculate slope. I am never going to have you calculate the slope along a curved line. You technically can do it, but it's kind of beyond the level of what we're doing in this class. So you're only going to have to do this with diagonal or horizontal lines, but obviously with a horizontal line, your slope is 0. So technically, this only gives you one option to say of 0 to 4 seconds. So we just want to double check that I'm not trying to trick you at all, and our slope here is indeed 2 meters per second. So we're going to do rise over run. So our rise here is 8, and our run here is 4. So 8 divided by 4 does equal 2 meters per second. So it is the answer for number 6 is 0 to 4 seconds, right? And all of these answers are written down on a answer key of the guided notes that you can find on Canvas as well. So if you have any questions, please let me know.